Diabetes, Understanding an Artificial Pancreas Threshold
By Adrian.
and Aberdeen.
Abstract. Type 1 diabetes is characterized by the autoimmune destruction of pancreatic beta cells, a challenge in regulating blood glucose levels, necessitating meticulous daily insulin management. The study aims to dive deep into the functionality of an artificial pancreas model through a closed-loop system, combining a continuous glucose monitor and a threshold controller. The primary objective is to investigate the efficiency of blood glucose level regulation using this model, with the focus on refining the artificial pancreas to support reliability and effectiveness. An aspect of this research involves constructing a conductivity sensor that employs a novel approach. By reducing the conductivity threshold with the addition of hands on the wires, a technique simulating decreased glucose levels, the model activates an Arduino-driven control mechanism, incorporating a fan to simulate insulin release.
Introduction. Type 1 diabetes, an autoimmune disease, targets the pancreas, hampering insulin production. Genetic and environmental factors, including viral infections, contribute significantly to its onset. Once activated, the body attacks and eliminates beta cells responsible for insulin generation, vital for facilitating the transfer of blood sugar into cells for energy. Insufficient insulin causes sugar accumulation, resulting in elevated blood sugar levels that damage the body, leading to various complications. Prevention remains elusive and triggers remain unclear. Although family history and age, particularly in juveniles, heightens susceptibility. Diagnosis involves blood tests for autoantibodies and urine tests for ketones. Unlike any other ailments, individuals manage type 1 diabetes with support from medical professionals, relying on daily insulin shots or pumps, regular blood sugar monitoring, prescribed diets, and healthy lifestyles to regulate glucose levels.
Problem. How do artificial pancreas thresholds work, and how can a model demonstrate their functions?
Purpose. Thresholds in an artificial pancreas are crucial for insulin regulation, using algorithms to monitor and adjust insulin based on glucose levels. A model showcasing glucose sensors, control algorithms, and insulin delivery illustrates how the system interprets glucose data and administers precise insulin doses, emphasizing thresholds' vital role in maintaining optimal blood sugar levels.
Hypothesis. When the Arduino-based system is appropriately configured and programmed to interpret analog sensor values and control the fan motor based on predefined thresholds, the fan motor's activation will mirror an artificial pancreas threshold mechanism. Consequently, the system's responsiveness will effectively correlate with changes in the analog sensor readings, similar to an artificial pancreas adjusting insulin levels in response to glucose measurements. This correlation will enable the system to regulate the fan's motor speed, turning both on and off, resembling the regulatory role of an artificial pancreas, and maintaining blood sugar levels with a specific range, thereby demonstrating its capacity to model artificial pancreas thresholds and environmental regulations. Variables are independent variables. Hardware components such as the fan motor, MOSFET, resistor, analog sensor, breadboard, Arduino board, jumper wires, and tools. Connection circuits, which include the arrangement and configuration of components following the circuit diagram, and the Arduino code itself, implementing and the structure of the code using the Arduino IDE.
Our dependent variables include system response, behavior of the fan monitor concerning analog sensor readings, the data collection, collected data from the system based on program logic, and the performance observations, assessment of how the system functions on base data and observations.
Controlled variables are power source, consistency in connecting the Arduino to a power source, computer via USB or battery using clips, program logic, maintaining the predefined thresholds and conditional statements regulating the fan motor, and observation and modification, the assessment of system behavior, code modifications, or hardware adjustments to achieve research objectives.
Our materials include the Arduino Uno solderless breadboard, a Grove mini fan and DC motor, a USB A/B cable, male jumper wires, 5V battery clip connector, and 100K mole resistor, and an N channel.
Procedure. First, we set up the hardware with the Arduino, we write the components to the Arduino, and we write the Arduino code.
Continuing the procedure, then you upload the code and run the experiment and analyze and iterate. And we'll go into details.
So here's our circuit diagram and a step-by-step on how to build the circuit. We have to connect the positive terminal of the fan to the motor to an external power source, and we either use the USB to a computer or a battery using a battery clip. Connect the negative terminal of the fan motor to the drain pin of the MOSFET. Connect the source pin of the MOSFET to the ground on the Arduino and the negative rail of the breadboard, and we connect the resistor to the Arduino board between the gate pin of the MOSFET and the digital pin, connect the positive rail of the breadboard to the 5V output of the Arduino, connect the negative rail of the breadboard to the ground of the Arduino, connect the analog sensor power VCC to the 5V output of the Arduino, and we connect the ground pin of the analog sensor to the ground of the Arduino, and connect the analog sensor output to the analog input pin on A0 onto the Arduino. So this is the code we used on our Arduino for our fan pump, and integer pump pin is 11, and this is the pin we use to control the pump with the two hands that we used. And then integer pump speed is 255 RPM, and this is as fast as the fan will go. And we had to declare conductivity, and this is between 0 to 1023 because we used a 5V, and our threshold is 900, and anything below will make the pump, which is the fan, turn off. This is a configuration code right here, and then this is where the code will run. So we have to read it at A0, which allows for the conductivity reading, and it will read it, and if the conductivity is less than 900, then the fan will turn off. And right here, the analog write allows us to see on the monitor what the threshold was at, which the fan turned off, and it turns the pump off if the threshold was reached.
So our pictures. So in figure 1, you can see the circuit board. This is where everything was and the pins that Adrian was saying. In figure 2, this is a code that we use in the model, and as my partner was saying, this is the monitor reading. Figure 3, this is us testing the threshold, and figure 4 is the experiment being successfully executed. This is our video. So our data tables show our results and the conductivity and response. So in our trial 1, we had 1023 analog volts, the hands were off, and the fan was on. So that means that the experiment worked. And in our second trial, the analog volts was lower till 895, and the hands were off, and there was no and the fan was off. And in trial 3, 892 analog volts with the hands on, and the fan was not turned on. And on trial 4, our final trial, there was 891 analog volts with hands on, and no conductivity was produced, and the fan was on.
So for our graphs, we have the conductivity read, and this is just a basic for each trial. And on this graph, it goes more in depth. So it tells you that this one had no hands on, and it was at a threshold of 1023. And when we had the hands on, it lowered the conductivity, lowering it to 895, 892, 891, which is less than 900, thus turning off the fan. And the analysis of our project sets out to create a smart system using Arduino that adjusts a fan on temperature thresholds to mimic those in an artificial pancreas. The connection of parts such as the fan, a special chip called MOSFET, and a sensor were added to the Arduino brain. The sensor works to measure the detection of human heat on the wires turning off with our hands on and turning on with hands off. The Arduino would turn the fan on or off on the detection of human heat. This mimics how our bodies work when sugar levels change. Just as an artificial pancreas knows when to release insulin in response to sugar levels, our system triggers the fan based on temperature changes. During our test, when it got warmer or cooler, the fan acted as it was supposed to, speeding up or slowing down. This showed how our system, like an artificial pancreas, can adapt and respond to changes, maintaining balance just like the body does with sugar levels. While our system is the basic model, it hints at how future smart systems could adapt and respond to such situations, much like how our bodies manage sugar levels to keep us healthy. A future of excitement, because smart systems could help in medicine and technology, making things work better in various environments.
This is our conclusion. Upon successful completion of the setup and code upload, the Arduino control pancreas model deactivates when the analog sensor value falls below the predetermined threshold. The system effectively demonstrates the ability to control the device based on real-time type 1 diabetes. The measurement blood sugar of 126 milligrams per deciliter or higher indicates diabetes. Our artificial pancreas model is defined as diabetes hitting a threshold of 1023 to 900, and anything less, meaning the insulin helps manage blood sugar levels. When a hand is placed on the wire, it acts as insulin injected into fat tissue underneath the skin, then gradually absorbed into the bloodstream. The fan turns off, indicating a reduction in the blood sugar levels and maintains the body's general.
Application. In the medical field, the Arduino-based system developed for controlling a fan motor based on analog sensor readings and predefined thresholds could find significant application in medical devices, particularly in therapeutic technology. The system's ability to mimic the function of an artificial pancreas threshold mechanism offers promising prospects in the development of closed-loop insulin delivery for individuals with diabetes. By adapting the technology to regulate drug delivery based on specific physiological parameters, it could contribute to the advancement of personalized medicine, ensuring precise and automated administration tailored to individual patient needs. This technology could be integrated into wearable medical devices, providing continuous monitoring and therapeutic interventions for various health conditions, thus enhancing patient care and management.
Further research. Closed-loop drug delivery systems. Expanding the system's capabilities to regulate drug delivery of various medications beyond insulin, allowing for automated dosing based on real-time physiological data. This research could explore applications in delivering other medications such as hormone therapy or pain management drugs, among others. Biomedical sensor integration. Integrating biomedical sensors capable of measuring a wider variety of physiological parameters to enhance the system's adaptability and responsiveness. Clinical trials and validation. Conducting clinical trials to assess the efficiency, safety, and usability of the developed system in the real-world medical setting. Miniaturization in wearable devices. Explore miniaturization of the system and the integration of wearable medical devices to facilitate continuous monitoring and treatment, improving patients' comfort and adherence to treatment regimens. Regulatory approval and commercialization. Pursuing regulatory approval processes and exploring pathways for commercialization to make this technology available